Every city on Earth has been under ice, not once, repeatedly, on a schedule so precise that scientists can calculate it going back millions of years. A slow, relentless rhythm of freeze and thaw, driven by tiny wobbles in the way our planet moves through space. We are living in one of the warm pauses between freezes. It is called the Holocene. It began 11,700 years ago, and inside it, all of recorded human history, every civilization, every empire, every invention, every language still spoken today, the pyramids, the printing press, the internet, all of it fits inside one warm window in an otherwise frozen world. That window has a pattern. The three most recent warm periods before this one each lasted around 12,000 years or less. We are already 11,700 years in. By that measure alone, the freeze should be thinking about returning. The same self reinforcing process that builds an ice age, where expanding ice reflects more sunlight, cooling the planet and allowing still more ice to grow, is also the mechanism that once drove Earth into a frozen world nearly 700 million years ago. Scientists call it Snowball Earth. The planet escaped, but only after millions of years. Now, here is where the story fractures. The science that should answer whether Earth is truly overdue for another ice age remains one of the most debated questions in modern paleoclimatology. The closer scientists look at it, the stranger and more unsettling the answer becomes. The ice has come back before, every time, without exception. The question is not whether it will come back. The question is whether the timetable is what anyone thinks it is. Some researchers believe comparisons with previous warm periods remain meaningful. Others argue they no longer apply. Tonight, we're not going to simplify that debate. We're going to follow the evidence wherever it leads, because the real answer turns out to be more surprising than either a simple yes or a simple no. If you'd like to see more stories like this, hitting like and subscribing is one of the best ways to support the channel. It really does make a difference. Settle in and let's continue. Stand for a moment on the shoreline of the present, and the warmth surrounding modern civilization begins to feel surprisingly unusual. The landscapes we know, the forests, rivers, coastlines, and fertile plains, belong to a brief chapter in a story that stretches across 4.5 billion years. Across that immense span, Earth has rarely remained steady for long. It has wandered through climates so warm that ice vanished from the poles, then drifted into periods of intense cold that reshaped entire continents. Around 50 million years ago, the planet looked strikingly different. The world was passing through the Eocene greenhouse, an interval when permanent polar ice had not yet formed. Crocodiles lived within the Arctic Circle. Palm trees flourished in what is now Alaska. Ocean waters carried warmth toward the highest latitudes, and snow struggled to survive from one year to the next. Compared with today's world, that distant Earth almost seems to belong to another planet, yet it formed the starting point of a gradual retreat toward colder conditions. The cooling unfolded with extraordinary patience. Beginning around 50 million years ago, temperatures declined across millions of years until Antarctica developed immense ice sheets roughly 38 million years ago. Those southern glaciers marked a profound turning point. Much later, between roughly 3 million and 2.5 million years ago, large ice sheets also appeared across the northern hemisphere. Earth had entered a new climatic state whose influence continues today. This is where language can become unexpectedly confusing. In everyday conversation, an ice age often means a time when glaciers spread across much of the land. Geologists use the phrase in two different ways. One describes a long interval lasting many millions of years, during which permanent ice exists at one or both poles. The other refers to shorter glacial periods within that larger framework, when continental ice sheets advance far beyond the polar regions before eventually retreating again during warmer interglacial intervals. By that geological definition, humanity still lives inside an ice age. Antarctica remains buried beneath permanent ice, preserving the condition that defines the present quaternary glaciation. The warmth surrounding civilization belongs to an interglacial, one of the milder pauses between major glacial advances, not the end of the larger frozen chapter itself. The quaternary began about 2.6 million years ago and continues into the present day. By around 800,000 years ago, its rhythm had settled into an extraordinary cycle. Long glacial intervals commonly stretched across about 100,000 years, followed by warmer interglacials lasting roughly 10,000 to 15,000 years, before colder conditions gradually returned once again. Much of this history comes from a remarkable archive hidden beneath Antarctica. Scientists drill deep into the ice, lifting long cylinders that preserve snowfall layered year after year across immense stretches of time. Tiny air bubbles trapped inside each layer contain fragments of ancient atmospheres, preserving chemical records from hundreds of thousands of years ago. Those frozen samples reveal temperatures, carbon dioxide levels, and the changing pulse of past climates with astonishing clarity. Every layer carries another page from Earth's memory. Reading those pages has transformed our understanding of ancient interglacials and the repeating cadence of advancing and retreating ice. Their message reaches far beyond the recent past, guiding the search toward an age when cold expanded across nearly the entire planet, leaving behind one of the most extraordinary chapters in Earth's history. Imagine a world where every horizon ended in ice, where every ocean carried a roof of frozen stone, and where the familiar blue of the planet disappeared beneath a brilliant white shell. More than 720 million years ago, during the cryogenian period, Earth entered one of the most extraordinary climates in its entire history. The planet froze. Rock formations preserved across several continents record this remarkable chapter, revealing a sequence of immense glaciations that reshaped the world on a scale unlike anything witnessed since. Geologists recognize several major freezing events within this distant past. Evidence points to the Magoниan glaciation, followed much later by the Sturtian and Marinian glaciations, which unfolded between roughly 850 million and 630 million years ago. Together, they form the foundation of what scientists call Snowball Earth. During these intervals, ice expanded far beyond the poles. It spread across the oceans until the frozen surfaces from each hemisphere met near the equator, enclosing almost the entire planet beneath an immense blanket of ice. The transformation may have unfolded across only thousands of years, a brief moment on geological timescales. Its engine was a process known as the albedo effect. Fresh ice reflects much of the sunlight that reaches it. As the frozen surface expanded, more sunlight bounced back into space instead of warming the ground and sea. Lower temperatures allowed still more ice to form. Every new layer increased Earth's brightness, and every increase in brightness encouraged additional cooling. The cycle strengthened itself without pause, carrying the freeze farther across the globe. Researchers believe even tropical oceans became sealed beneath extraordinary thicknesses of ice. In some places, that frozen cover may have reached several hundred meters, which is about 984 feet. Sunlight struggled to reach the waters below, while winds swept across an almost continuous frozen landscape. The mechanism behind this event belongs to the distant past, yet it remains familiar. Every glacial period depends upon the same feedback. Expanding ice reflects more sunlight, encouraging conditions that allow the frozen margins to continue advancing. For millions of years, the frozen shell endured, while another process continued almost unnoticed. Volcanoes remained active beneath the ice and along the ocean floor, releasing carbon dioxide into the atmosphere. Under ordinary conditions, rainfall would have dissolved much of that gas and carried it into rivers and oceans. During Snowball Earth, widespread frozen seas disrupted that balance. Carbon dioxide accumulated gradually overhead, remaining in the atmosphere as volcanic eruptions continued across immense stretches of time. Eventually, the concentration of carbon dioxide became great enough to strengthen the greenhouse effect beyond the power of the reflective ice. Temperatures climbed little by little until melting began. Dark water appeared where brilliant ice had once reflected sunlight away. Those newly exposed oceans absorbed increasing amounts of solar energy, accelerating the thaw. The same feedback that had driven freezing now worked in reverse, allowing the world to emerge from one of its deepest climatic extremes. Even the last glacial maximum, remarkable in its own right, reached nothing close to this scale. At its greatest extent, continental ice covered only about 8% of Earth's surface, and that condition lasted for a comparatively brief interval beside the immense duration of the Sturtian glaciation. The difference stretches beyond ordinary comparison. When the frozen shell finally yielded, the transformed world opened a path toward one of the greatest turning points in the history of life. Shaped in part by the long dominion of ice, life did not return to the thaw as the same world that had entered the freeze. Across the immense span of Snowball Earth's icy dominion, survival belonged only to organisms capable of enduring extraordinary environmental stress. Every generation that persisted carried solutions shaped by scarcity, chemistry, and endurance. When warmth finally spread across the planet once more, those survivors became the foundation for a transformation that changed the history of life forever. Before those glaciations, Earth had spent billions of years ruled almost entirely by microscopic organisms. Single-celled life filled warm, shallow seas, carrying out the slow work of growth and reproduction and evolution across intervals almost impossible to imagine. Colonies of bacteria and other simple organisms gradually altered the atmosphere and oceans, preparing conditions that more complex forms of life would eventually inherit. Progress unfolded with remarkable patience, measured across countless generations rather than dramatic leaps. The prolonged freeze interrupted that ancient rhythm. Habitats disappeared beneath ice, sunlight reaching the oceans became scarce, and familiar ecological relationships collapsed. Many organisms vanished, while others survived in isolated pockets where conditions remained suitable for life. The survivors were shaped by relentless environmental pressure. Adaptations that once offered only slight advantages became essential for persistence. Every surviving lineage represented a long chain of successful responses to an unforgiving world. When the ice retreated, the landscape released an unexpected gift. Glaciers had ground enormous quantities of rock into fine sediment, rich in iron, phosphorus, and other minerals. Flowing water carried those nutrients into the oceans, where they mixed with waters once again exposed to sunlight. Marine ecosystems suddenly possessed abundant raw materials for growth. Photosynthetic organisms flourished, food webs expanded, and ecological opportunities multiplied across seas that had remained constrained for millions of years. Around 541 million years ago, the fossil record changed with astonishing speed. Paleontologists call this interval the Cambrian explosion because nearly every major animal body plan known today appeared within a comparatively brief geological period. Creatures evolved hardened shells that offered protection against predators. Eyes capable of detecting light with increasing precision transformed the search for food and the avoidance of danger. Limbs and jointed appendages allowed animals to crawl, swim, burrow, and explore environments that earlier life had never occupied. Jaws emerged, opening entirely new ways of feeding and creating the first enduring relationships between predator and prey. This flourishing of complexity has often been linked, at least in part, to the environmental reset created by the closing Snowball Earth glaciation. The relationship remains an active area of scientific study, yet the timing is compelling. Ice stripped ecosystems to their essentials, while the returning warmth replenished oceans with nutrients and energy. The combination created conditions unlike those that had existed before the freeze. An irony runs through this chapter of Earth's history. The warming that finally ended Snowball Earth depended upon volcanic carbon dioxide accumulating across millions of years. The same gas that dominates modern climate discussions once played a central role in lifting the planet from one of its deepest frozen states, reminding us that its influence has always been woven into Earth's changing climate. From that remarkable beginning, life continued to diversify through warmer intervals, smaller glaciations, shifting continents, and great extinctions. Forests spread across the land, oceans filled with unfamiliar creatures, and ecosystems grew steadily richer until, hundreds of millions of years later, another great age of ice arrived, leaving behind a legacy that would eventually fuel human civilization itself. Another frozen chapter arrived hundreds of millions of years after the first great flourishing of complex life. Across an interval stretching from roughly 350 million to 260 million years ago, glaciers expanded again across large portions of the southern world. Geologists call this prolonged episode the Karoo glaciation. It may have been the longest glacial interval known, beginning during the closing stages of the Devonian period, continuing through the entire Carboniferous, and extending well into the Permian. While ice accumulated across the far south, the equatorial regions presented an entirely different landscape. The Carboniferous world, between about 360 million and 300 million years ago, supported immense swamp forests, unlike anything alive today. Towering club mosses, giant horsetails, and primitive trees rose into warm, moisture-filled air. Their heights rivaled modern skyscrapers, creating layered forests where sunlight filtered through dense canopies onto wetlands rich with plant life. Animals also reflected the unusual atmosphere of this age. Oxygen reached about 35% of the air, nearly 70% higher than modern levels. Such conditions allowed some insects to attain extraordinary proportions. Dragonflies crossed the skies with wingspans approaching zero point 0.6 meters, which is about 2 feet. Amphibians flourished in marshes and winding channels, while forests spread across broad tropical lowlands that circled much of the equator. One remarkable detail distinguished these forests from those of the modern world. The organisms capable of efficiently breaking down lignin, the tough material that gives wood its strength, had not yet become widespread. Fallen trunks and branches accumulated faster than they decomposed. Layer upon layer settled into waterlogged ground where oxygen remained scarce. Buried beneath sediments, those immense deposits slowly transformed under heat and pressure, becoming coal across millions of years. Far from those humid forests, the southern supercontinent of Gondwana carried expanding ice sheets across lands that would later become South America, Africa, Antarctica, India, and Australia. This glaciation shaped sea levels, altered rainfall, and influenced ecosystems around the globe. Warm equatorial wetlands and polar ice existed together within the same planetary system, each responding to Earth's changing geography and atmosphere across immense spans of time. The connection to the present reaches directly through those buried forests. Coal, extracted during the Industrial Revolution and afterward, consists largely of compressed Carboniferous vegetation. Those ancient plants absorbed carbon dioxide from the atmosphere during their lifetimes, storing its carbon within trunks, roots, and leaves. Geological processes locked that carbon underground across hundreds of millions of years. Burning coal releases it again within only a few centuries, returning to the atmosphere material that nature had removed over incomparably longer intervals. Eventually, the balance supporting the Karoo glaciation shifted. Continents continued their restless movement. Volcanic activity altered atmospheric chemistry, and the gradual breakup of the supercontinent Pangaea transformed global circulation. Those combined changes weakened the climatic conditions that favored extensive ice sheets. Temperatures climbed, glaciers withdrew, and Earth entered one of its longest sustained warm intervals. That warmer world became the stage upon which the dinosaurs would later thrive for tens of millions of years. Forests changed, oceans evolved, and continents drifted into new positions beneath a climate far milder than the glacial age before it. The path toward the frozen world that eventually shaped humanity would begin much later, set in motion by a geological change whose influence reached far beyond the place where it first appeared. Sometimes the greatest changes begin with a strip of land so narrow that it seems almost insignificant on a world map. Across millions of years, continents drifted little by little until a final connection emerged between North America and South America. That slender bridge altered the movement of oceans, reshaped atmospheric circulation, and gradually guided Earth toward the glacial rhythm that still defines the present age. Evidence recovered from deep sea sediment cores reveals that Earth's climate had already been cooling since around 50 million years ago. Layer after layer of ancient seafloor preserves microscopic shells and chemical signatures, recording steadily falling temperatures across immense spans of geological time. The process unfolded gradually, preparing the planet for another major climatic transition. By roughly 3 million to 2.5 million years ago, large ice sheets finally began appearing across the northern hemisphere, marking the beginning of a familiar pattern of advancing and retreating ice. One event appears to have played an especially important role in that transformation. Between about 3 million and 2.8 million years ago, the final closure of the Isthmus of Panama completed the land bridge linking the two American continents. Before that connection formed, warm equatorial waters flowed freely between the Atlantic Ocean and the Pacific Ocean. Heat spread more evenly around the globe, and the far north remained comparatively mild. As the passage closed, the circulation of the oceans changed in remarkable ways. Warm, salty Atlantic waters could no longer escape easily into the Pacific. Powerful currents carried increasing amounts of that warmth northward instead. At first glance, such a shift seems as though it should have reduced the likelihood of widespread glaciation. Yet the climate system responded in a more intricate fashion. Warmer ocean water evaporated readily, filling the atmosphere with greater amounts of moisture. Winds transported that moisture toward high northern latitudes where colder conditions transformed it into snowfall. Each winter left fresh layers across Arctic landscapes. If enough of that snow survived the following summer, it accumulated year after year. Thin seasonal coverings slowly developed into permanent ice fields, and those ice fields gradually expanded into continental ice sheets. The sequence carried an elegant paradox. Extra warmth delivered to the north ultimately encouraged the growth of ice. Moisture proved more important than temperature alone. Fresh snowfall increased the brightness of the surface, reflecting greater amounts of sunlight back into space. Cooler conditions favored additional snow, strengthening the same self reinforcing process that had shaped frozen worlds much earlier in Earth's history, though on a far smaller scale. Around 2.6 million years ago, the Quaternary glaciation began, and it continues today. Unlike earlier prolonged freezes, this era did not consist of one uninterrupted blanket of ice. It unfolded as a succession of glacial periods and warmer interglacials. Ice sheets advanced across continents, then withdrew. Sea levels dropped as water became locked within glaciers, then rose again as the ice melted. Habitats shifted, species adapted, populations disappeared, and new forms of life spread into changing landscapes. Every pulse altered coastlines, rivers, forests, and grasslands. Continents remained recognizable, yet their appearance transformed repeatedly as ice expanded and retreated across thousands of years. The world became a place of recurring movement instead of permanent stability, with climate following a rhythm that would eventually shape the environment into which human beings emerged. That rhythm did not arise by chance. It followed an underlying pattern whose timing remained hidden for millions of years, waiting for someone patient enough to uncover the mathematics guiding the rise and retreat of the ice. Long before powerful computers could simulate climates across geological time, one mathematician chose to solve an almost unimaginable problem using little more than paper, equations, patience, and persistence. Milankovitch, a Serbian mathematician and astronomer born in 1879, believed that the changing rhythm of Earth's climate could be understood through the language of celestial motion. His ambition reached far beyond the weather of a season or even the climate of an age. He wanted to calculate how sunlight had fallen across every latitude of Earth through the previous 600,000 years. The work demanded extraordinary precision. Every calculation had to account for the subtle movements of a planet traveling through space while rotating upon its axis. During the early years of the 20th century, this required years of careful mathematics performed entirely by hand. Tables filled with numbers gradually became a portrait of Earth's changing relationship with the Sun, revealing patterns so slow that no human lifetime could ever witness them directly. History soon interrupted his research. When the First World War began in 1914, the Austro-Hungarian army captured Milankovitch while he was traveling during his honeymoon. Circumstances could easily have ended his scientific work. Instead, a colleague intervened on his behalf, allowing him to remain under house arrest in Budapest, where he gained access to a library. Surrounded by books instead of laboratory instruments, he continued filling pages with calculations while conflict unfolded across Europe. Those years produced one of the most influential ideas in paleoclimatology. Milankovitch recognized that Earth follows neither a perfectly circular orbit nor a perfectly upright spin. The direction of its axis also changes through time. Each of these motions unfolds gradually and predictably, altering how sunlight is distributed across the planet over thousands of years. The total amount of energy reaching Earth changes very little, yet its seasonal and geographical distribution shifts enough to influence the growth and retreat of great ice sheets. His calculations focused especially on summer sunlight reaching the high northern latitudes. Winter snowfall alone could never create continental glaciers if every summer melted it away. The crucial factor was whether cool summers allowed patches of snow to survive from one year into the next. Surviving snow gradually accumulated, compressed into ice, and expanded across the landscape through countless seasons. A slight alteration in summer sunlight could therefore influence climates over entire continents. Milankovitch devoted decades to refining these calculations, publishing results that initially received only limited attention. Many scientists admired the mathematical elegance of his work, while remaining uncertain that orbital changes alone could explain the timing of repeated glacial cycles. Confirmation would require evidence extending far beyond recorded history, evidence unavailable during his lifetime. That evidence eventually emerged from Greenland and Antarctica. Deep ice cores preserved detailed climate records stretching back hundreds of thousands of years. Their layered history revealed a remarkable correspondence between recurring glacial cycles and the orbital variations Milankovitch had calculated decades earlier. Independent studies strengthened the connection until the theory became widely accepted, including by the National Research Council of the United States National Academy of Sciences. The rhythm he uncovered reaches through every frozen landscape discussed so far. Behind advancing glaciers, retreating ice sheets, and shifting coastlines lies a slow celestial choreography. Earth's orbit, its axial tilt, and its gradual wobble work together as an enduring clock, guiding the climate with a patience measured across geological time. Earth's journey around the sun appears steady from the perspective of a human lifetime. Sunrise follows sunrise, seasons return in familiar order, and the sky offers little hint that the planet's motion is changing at all. Across tens of thousands of years, however, that motion slowly shifts. Three separate orbital cycles move together with extraordinary patience, adjusting how sunlight reaches different parts of the world and guiding the long rhythm of advancing and retreating ice. The first of these cycles is called eccentricity, the gradual change in the shape of Earth's orbit around the Sunday. The orbital path is never a perfect circle. It stretches into a gentle ellipse and later becomes more circular again across a cycle, lasting roughly 100,000 years. When the ellipse becomes more pronounced, the difference between Earth's closest and most distant positions from the Sun increases. That subtle alteration changes the distribution of solar energy received during the year, adding another layer to the planet's long climatic rhythm. The second cycle is obliquity, also known as axial tilt. This describes the angle at which Earth's rotational axis leans relative to the plane of its orbit. Today, that tilt measures about 23.5 degrees. Across roughly 41,000 years, it shifts between about 22.1 degrees and 24.5 degrees. A greater tilt produces stronger seasonal contrasts, bringing warmer summers and colder winters to high latitudes. A smaller tilt softens those seasonal differences, allowing cooler summers that make it easier for winter snow to survive. The third cycle is precession, the gradual wobble of Earth's rotational axis. A spinning top provides a familiar comparison as its axis traces a slow circle before settling. Earth behaves in a similar manner, completing one full wobble in approximately 26,000 years. This movement determines which hemisphere points more directly toward the Sun during different stages of Earth's orbit, altering the seasonal distribution of incoming sunlight. Together, these three cycles modify the amount of solar energy reaching Earth's middle latitudes by as much as 25% across long intervals. Their combined influence is far greater than any single cycle acting alone. Every adjustment is gradual, almost imperceptible across generations, yet powerful enough to reshape continents when measured across geological time. The crucial detail lies in where and when that sunlight arrives. Ice ages are not controlled primarily by the total amount of energy reaching Earth. Summer sunlight in the high northern latitudes holds the greatest importance because most of the planet's northern landmass occupies those regions. When summers remain cool enough that winter snow does not melt completely, fresh snowfall arrives the following winter before the previous layer disappears. The accumulated snow compresses into ice, glaciers expand, and continental ice sheets slowly begin their advance. According to Milankovitch theory, prolonged periods of weak summer sunlight across the high northern latitudes create the conditions necessary for a new glacial cycle to begin. Yet one important observation complicates the idea that another ice age should already be underway. Summer insolation during the Holocene has already reached its minimum, but no widespread glacial inception has appeared, despite the repeating 100,000-year rhythm observed across the last 800,000 years. That puzzle reaches even deeper. Around 800,000 years ago, the dominant rhythm of glacial cycles shifted from roughly 41,000 years to about 100,000 years, closely matching the eccentricity cycle. Scientists still debate why that transition occurred. The orbital clock provides the framework, though its complete story remains preserved within Antarctica's oldest ice. Across Antarctica, snow has fallen season after season for hundreds of thousands of years. Each snowfall settled upon the last, forming delicate layers that were gradually buried by fresh accumulations. The growing weight squeezed loose crystals together until the snow transformed into dense ice. Tiny pockets of the surrounding atmosphere became sealed inside. Those trapped bubbles remained protected from the changing world above, preserving the composition of ancient air exactly as it existed when each layer first settled onto the frozen surface. That remarkable process turned the Antarctic ice sheet into something unlike any other natural archive. Every layer marked another passing year, while every enclosed bubble carried a direct sample of Earth's former atmosphere. Scientists no longer had to rely only on rocks, fossils, or sediments to reconstruct distant climates. By drilling into the ice itself, they could recover pieces of the sky from ages that vanished long before human history began. The deepest ice cores recovered from Antarctica extend back approximately 800,000 years. They preserve a record that reaches more than 700,000 years before the appearance of our own species. Near the surface, the youngest layers speak of comparatively recent centuries. Far below, the oldest sections reveal climates that unfolded while continents, oceans, and living creatures occupied worlds entirely unfamiliar to us. Each additional meter descended through the ice represents another step backward across immense stretches of time. Among these extraordinary records, the European project for ice coring in Antarctica Dome, Charlie Core, stands apart. This cylinder of ice extends about 3,270 meters, which is about 10,728 feet, from the surface to the deepest recovered layer. Every portion demanded immense effort to retrieve without disturbing the fragile bubbles enclosed within. The scientists who lifted those frozen cylinders from the Antarctic interior were reading messages assembled gradually across almost 1 million years. Those messages revealed an unmistakable pattern. Across every complete glacial cycle preserved within the record, atmospheric carbon dioxide and global temperature rose and fell together. During colder intervals, carbon dioxide concentrations declined, while enormous ice sheets expanded across the northern hemisphere. During warmer intervals, Carbon dioxide increased as glaciers retreated and climates softened. The timing was not perfectly synchronized. At different moments, one change slightly preceded another. Even so, the partnership remained visible throughout 8 complete glacial cycles, repeating with remarkable consistency. The measurements also revealed the range within which this partnership operated. During the coldest glacial periods, atmospheric carbon dioxide fell to roughly 180 parts per million. During warmer interglacial periods, such as the present natural state before industrial influence, concentrations reached approximately 280 parts per million. Today, the atmosphere contains more than 420 parts per million, exceeding anything preserved within the 800,000 year Antarctic record and surpassing levels not observed for millions of years, according to broader geological evidence. These findings demonstrate that carbon dioxide is more than a companion to changing temperatures. It acts as a powerful amplifier within Earth's climate system. Lower concentrations favor the growth and persistence of continental ice sheets. Higher concentrations strengthen warming that discourages widespread glaciation. The ice does not describe a single cause acting alone. Instead, it preserves an intricate conversation between sunlight, oceans, atmosphere, and frozen continents, written patiently into layer after layer until the close of the last great glacial age about 11,700 years ago. The shape of the world was once so different that many familiar coastlines had not yet been drawn. Between roughly 29,000 and 19,000 years ago, Earth reached the last glacial maximum, the coldest stage of the most recent glacial period. Ice sheets and glaciers covered about 8% of the planet's surface, while sea level stood approximately 125 meters, which is about 410 feet, lower than today. Entire landscapes that now rest beneath shallow seas formed continuous plains connecting distant regions. Across North America, the Laurentide ice sheet spread over more than 13 million square miles, extending south to about latitude 37 degrees north. Another immense ice sheet stretched across Britain, Ireland, Scandinavia, and much of northern Europe, covering around 6,600,000 square miles. Antarctica remained buried beneath permanent ice, while glaciers occupied the Himalaya and the southern reaches of Patagonia. Frozen water had gathered into continental masses of astonishing scale, reshaping weather, rivers, and coastlines across much of the globe. The ice itself was a landscape, rising far above the ground it concealed. Near what is now Chicago, its thickness exceeded 1,500 meters, which is about 5,000 feet. Around present-day Toronto, it approached 2,440 meters, which is about 8,000 feet. Such extraordinary weight pressed the underlying bedrock downward. Even today, more than 11,000 years after those glaciers withdrew, parts of Canada and northern Europe continue their gradual upward rebound as the crust slowly recovers from that immense burden. Cold alone did not define this world. Much of the atmosphere contained less moisture because enormous quantities of water remained locked inside glaciers. Vast regions became dry, with sparse vegetation and expanding deserts. Winds lifted fine sediments from exposed plains and carried them across continents. This glacial dust, known as loess, settled into thick deposits that would eventually become some of the richest agricultural soils on Earth. The airborne dust also reflected additional sunlight and influenced temperatures far beyond the edges of the great ice sheets. Lower seas transformed geography in remarkable ways. Dry land joined Siberia to Alaska, providing a broad corridor between Asia and North America. Britain remained connected to continental Europe, making it possible to travel across open ground between what are now London and Paris. Land also linked Asia Minor to the Greek peninsula, Korea to Japan, and Denmark to Sweden. Coastlines extended far beyond their modern limits, revealing plains that have since disappeared beneath rising oceans. Much of northern Eurasia formed an immense belt of open steppe stretching from France across the continent toward China. Forests retreated from many regions, replaced by hardy grasses, scattered shrubs, and hardy flowering plants adapted to brief summers. Permafrost extended across areas that now support fertile farmland in the American Midwest. Rivers followed unfamiliar routes through exposed valleys, while glaciers carved fresh basins that later filled with water to become countless modern lakes. Although this frozen earth appears distant from the present, it remained vibrant with life. Plants, animals, and human communities adapted to conditions that shaped every migration and every season. The land demanded resilience, yet it also created opportunities wherever ice, wind, and water opened new pathways. The world was colder, drier, and broader than the one we know today, a place where immense glaciers governed the rhythm of every horizon, while life continued to find its place across an altered planet. Across the broad plains left behind by retreating forests, the cold favored animals of remarkable size. The Pleistocene landscape supported great herds of mammals whose bodies were shaped by freezing winters, dry grasslands, and seasons that demanded endurance. They wandered across continents that were linked by exposed land, following routes that stretched from Western Europe through Northern Asia and into North America. Their footprints marked one of the richest chapters in the history of large land animals. Among them walked the woolly mammoth, perhaps the defining creature of the Ice Age. Adults commonly stood about 3 to 3.7 meters tall, which is about 10 to 12 feet, at the shoulder and weighed between about 5,400 and 7,300 kilograms, which is about 12,000 to 16,000 pounds. Dense fur covered its body, while a thick layer of fat helped preserve warmth through severe winters. Its sweeping tusks curved forward in broad arcs, serving as tools for clearing snow, moving vegetation, and competing with rivals across the open steppe. Nearby grazed the woolly rhinoceros, another giant built for frozen landscapes. Adults weighed around 3,600 kilograms, which is about 8,000 pounds, giving rise to the familiar estimate of 4 tons. A long front horn often exceeded 1 meter, which is about 3.3 feet, allowing the animal to scrape snow away from hardy grasses that remained buried through much of the winter. Its heavy coat, compact ears, and powerful shoulders reflected countless generations adapting to conditions that challenged nearly every other form of life. Predators matched the scale of their prey. The cave lion was approximately 1/4 larger than the modern African lion, possessing longer limbs and a powerful frame suited to pursuing large herbivores across open country. Steppe bison gathered in immense herds, their broad heads and muscular shoulders enabling them to sweep aside snow in search of forage. Towering above many other grazers stood the Irish elk. The antlers of mature males reached nearly 3.7 meters across, which is about 12 feet, the widest antlers known from any animal that has ever lived. Their immense displays transformed seasonal breeding grounds into extraordinary spectacles. These animals belong to the mammoth steppe, an immense belt of cold, dry grassland extending across Eurasia and into North America during the last glacial maximum. Although temperatures remained low, This biome ranked among the most productive ecosystems ever known in terms of animal biomass. Grasses, flowering plants, and hardy herbs supported astonishing numbers of grazing mammals, which in turn sustained formidable predators. The exposed land bridge between Siberia and Alaska allowed populations to move freely between continents, maintaining one of Earth's greatest interconnected wildlife communities. Even after glaciers retreated and many populations disappeared, the woolly mammoth endured in isolated refuges. One of the last groups survived on Wrangel Island until about 3,700 years ago. That island had remained connected to northeastern Asia until approximately 12,000 years ago, when rising seas separated it from the mainland. Isolation delayed extinction, preserving a final population long after mammoths had vanished elsewhere. Their disappearance remains one of prehistory's enduring puzzles. North America lost roughly 70% of its large mammals, Eurasia about 40%, South America around 80%, and Australia nearly 90%. Climate change, expanding human hunting, and disease have each been proposed as contributing forces. Current evidence suggests these pressures overlapped during a period of rapid environmental transformation, reshaping ecosystems across the world. Amid those sweeping changes, one adaptable primate continued spreading across the changing landscape, carrying its future into every continent, the ice made reachable. Among all the creatures shaped by the great glacial cycles, one species responded in a way no other ever had. Homo sapiens did not merely adapt its body to changing climates, it transformed behavior into its greatest survival tool. As temperatures fell and landscapes shifted, people fashioned bone needles capable of stitching fitted clothing from animal hides. Carefully sewn garments trapped warmth far more effectively than wrapped skins, allowing families to remain active through winters that would have challenged even well-adapted mammals. Life demanded planning that extended far beyond the present season. Communities learned where migrating herds would appear, where edible plants emerged after thaw, and where stones suitable for tools could be gathered. Knowledge passed from one generation to the next became as valuable as food itself. Every successful hunt, every carefully prepared shelter, and every improved spear point added another layer to a growing inheritance of practical skill. Survival became an exercise in memory, cooperation, and patient observation. Far to the west, modern humans living in what is now France left another kind of inheritance. During the last glacial maximum, groups often known as the Cro-Magnons entered limestone caves and covered their walls with astonishing paintings. At Chauvet and Lascaux, horses, bison, rhinoceroses, lions, and mammoths appear with striking anatomical precision and graceful movement. These works were created while glaciers still dominated much of the northern hemisphere. They reveal people whose lives contained artistry alongside endurance, imagination alongside daily survival. The lowering of sea level reshaped more than coastlines. It opened routes that no longer exist. Between northeastern Asia and Alaska stretched Beringia, a broad landmass roughly comparable in size to modern Australia. This was not a narrow bridge crossing frozen water. It was an expansive region of grassland, rivers, and grazing animals. Herds of mammoths, steppe bison, horses, and other large mammals crossed its open plains over countless generations. Human communities eventually followed the same pathways, entering North America across ground that now lies beneath the Bering Sea. The recent Ice Age, therefore, became one of the great engines of human expansion. Lower seas exposed additional land bridges linking territories that are now divided by water. Step by step, generation after generation, people spread outward from their place of origin until they occupied 6 of the 7 continents that exist today. Travel unfolded across centuries, guided by changing climates, migrating animals, and newly accessible landscapes created by advancing and retreating ice. These migrations also altered the balance of life around them. As humans entered unfamiliar ecosystems, many encountered giant mammals that had never faced such adaptable hunters. Some researchers conclude that expanding human populations contributed to the disappearance of species, including the woolly mammoth and the giant ground sloth. Others emphasize rapidly changing climates as glaciers withdrew. Additional studies consider disease and ecological disruption. Present evidence suggests that several pressures acted together during a time of sweeping environmental change, making a single explanation unlikely. The demands of glacial living may also have influenced the development of human thought. Enduring long winters encouraged planning months ahead, careful sharing of resources, increasingly refined tools, and close cooperation within groups. Some researchers suggest these persistent challenges favored greater cognitive flexibility, strengthening abilities that later supported agriculture, navigation, language, and complex societies. When the glaciers finally withdrew, they left behind more than valleys, lakes, and fertile plains. They also left a world entering an unusually stable interval, a climate gentle enough for villages to become cities, fields to replace wandering camps, and civilization to take root upon ground prepared by ice. The Great Retreat of the Ice did not arrive as a single dramatic moment. Across many generations, glaciers withdrew toward higher latitudes, rivers found new paths, and valleys filled with fresh water. Around 11,700 years ago, Earth entered the Holocene, the present interglacial interval. It marked the beginning of an unusually warm chapter after the long grip of the last glacial period, opening conditions unlike those experienced for much of the preceding 2.5 million years. As the frozen reservoirs melted, coastlines transformed. Global sea level climbed by roughly 120 meters, which is about 394 feet, drowning plains that had once connected distant lands. Beringia disappeared beneath the sea. Britain became separated from continental Europe. Shorelines shifted inward across every ocean basin. Forests steadily expanded into regions where tundra had previously stretched across the landscape, while rainfall patterns became more favorable across many temperate zones. Rivers stabilized, wetlands formed, and fertile floodplains emerged where people would later establish permanent settlements. The greatest gift of the Holocene was not warmth alone. Earth had experienced warmer interglacial intervals before. What distinguished this one was its remarkable stability. Temperatures fluctuated within comparatively narrow limits over thousands of years. Growing seasons became dependable across long stretches of time. Rains generally returned in familiar rhythms. The changing of the seasons still unfolded, yet the larger climate no longer lurched between dramatic extremes that could erase generations of careful adaptation. Predictability became one of the most valuable natural resources the planet had ever offered. Human communities responded with extraordinary speed. Around 10,000 years ago, people in several parts of the world began cultivating plants and managing animals instead of relying entirely upon hunting and gathering. Reliable harvests encouraged families to remain in one place for longer periods. Villages expanded into permanent settlements, and stored food supported increasing populations. Fields replaced wandering routes, while seasonal observation became the foundation of farming calendars that reached from one generation to the next. Agriculture emerged independently across at least 7 different regions during this favorable interval. The Fertile Crescent nurtured wheat and barley. Communities in China cultivated rice and millet. Farming appeared in New Guinea, Mexico, the Andes, the eastern United States, and West Africa through separate traditions shaped by local plants and landscapes. These societies were separated by immense distances and had no knowledge of one another, yet each responded to a world whose climate had become unusually dependable. The near parallel timing reflects an opportunity presented on a planetary scale. From those farming communities grew nearly everything associated with civilization. Cities rose beside rivers. Writing preserved memory beyond a single lifetime. Mathematics measured harvests and stars alike. Architecture reshaped stone into monuments. Music, philosophy, medicine, trade, and organized government flourished within societies that no longer needed to move constantly in pursuit of food. Every chapter of recorded history unfolded inside the same extended interval of climatic steadiness. For this reason, the Holocene is often described as the age of humans. Every empire, every library, every voyage across the oceans, every scientific discovery, and every technological revolution belongs entirely within these 11,700 years. Compared with the immense sweep of geological time, it is an exceptionally brief interval. Its very brevity gives rise to a remarkable observation. The stable climate supporting civilization has already endured for 11,700 years. Within the rhythm of Earth's recurring glacial cycles, that duration naturally invites a deeper examination of whether this unusually favorable window is following the pattern established by the planet's distant past. A pattern begins to emerge when the ice core record is viewed as one continuous archive instead of a collection of isolated climates. Warm intervals appear, flourish for a time, and eventually give way to expanding ice. Across the last 800,000 years, this rhythm repeats often enough that it naturally invites comparison with the present. The comparison is valuable, provided each piece of evidence is weighed with equal care. The three interglacial periods that preceded the Holocene, known to paleoclimatologists as marine isotope stage 5, marine isotope stage 7, and marine isotope stage 9, each endured for roughly 12,000 years or less before colder conditions gradually returned. The Holocene has now continued for approximately 11,700 years. Looking only at those examples, it is understandable why some observers conclude that another glacial advance should already be close. Measured by age alone, describing the present interglacial as overdue may appear reasonable. The difficulty begins when age is treated as a countdown. Ice ages do not arrive because an interglacial has existed for a particular number of years. They begin only when orbital conditions favor the survival of winter snow through successive northern summers. If enough snow escapes melting, each passing year adds another layer. Ice sheets expand gradually across the landscape. Without those orbital circumstances, the calendar itself carries little predictive power. The ice core record illustrates this clearly. Interglacial periods have not followed a uniform schedule. Some lasted roughly 10,000 years before cooling resumed. Others extended beyond 28,000 years. Their durations varied because Earth's orbit, axial tilt, and rotational wobble never combined in exactly the same way from one cycle to the next. Every interglacial inherited its own astronomical starting conditions, and those conditions shaped how long the warm interval could persist. This distinction also provides a useful lesson in scientific communication. A statement can begin with an accurate observation, yet still lead toward a misleading conclusion. It is entirely correct that the Holocene has already lasted as long as several earlier interglacials. It does not automatically follow that Earth has exceeded a fixed deadline for entering another ice age. That implication sounds precise because it compares familiar numbers, yet the comparison overlooks the factor that actually governs glacial inception. The result is a conclusion that appears stronger than the underlying evidence allows. The more dependable way to frame the question begins elsewhere. The age of the Holocene represents one point of information within a much larger system. Orbital geometry carries greater weight because it determines how much summer sunlight reaches the high northern latitudes, where continental ice sheets either disappear or endure. Modern calculations show that today's orbital configuration differs substantially from those associated with several shorter interglacials preserved within the Antarctic record. Those differences cannot be ignored when evaluating Earth's future trajectory. Rather than asking whether the Holocene has reached an expected ending, paleoclimatologists first examine whether the present astronomical conditions resemble the conditions that accompanied previous glacial beginnings. That comparison reaches beyond simple chronology into the mechanics of the planet itself. Among all the warm intervals preserved within the ice, one stands apart as an especially revealing parallel. Its combination of orbital conditions bears an unusually close resemblance to our own, offering one of the clearest natural experiments available for understanding where the present interglacial may yet lead. Among the many warm intervals preserved within the Antarctic ice record, one has drawn particular attention for decades. It unfolded around 400,000 years ago and is known as marine isotope stage 11. To paleoclimatologists, it is more than another chapter in Earth's climate history. Its orbital arrangement bears an unusual resemblance to the one surrounding the present Holocene, making it one of the most carefully examined natural comparisons available for understanding our own interglacial. Marine isotope stage 11 began with a relatively rapid warming before settling into a remarkably prolonged period of climatic stability. Instead of slipping back toward glacial conditions after roughly 12,000 years, as several other interglacials had done, it continued for about 28,000 years. Temperatures gradually leveled rather than climbing endlessly, creating a sustained warm interval that persisted far longer than many neighboring cycles preserved in the geological record. The reason this interval attracts such attention lies beyond temperature alone. Calculations of Earth's orbital geometry indicate that the combination of eccentricity, axial tilt, and precession during marine isotope stage 11 closely resembles the astronomical configuration surrounding the present day. Because the orbital forcing is so similar, some researchers argue that the Holocene may naturally follow a comparable path. Under that interpretation, the warm interval that began around 10,000 years ago could continue for another 15,000 to 20,000 years, even in the absence of any additional influence from human-released carbon dioxide. This comparison offers a striking alternative to the familiar claim that Earth has already delayed its next ice age. If marine isotope stage 11 provides the best guide, then the present interglacial may still occupy the earlier half of its natural lifespan. The apparent similarity suggests that orbital conditions alone could sustain relatively mild climates for many thousands of years before northern summers eventually become cool enough to support persistent continental ice growth. The evidence, however, does not point in only one direction. Another warm interval, marine isotope stage 19, also shares several important orbital characteristics with the Holocene. Its history unfolded differently. Following its initial warming, cooling resumed comparatively early, and the interglacial proved much shorter than marine isotope stage 11. Although the orbital similarities remain meaningful, they did not produce an equally prolonged warm period. That contrast reminds researchers that Earth's climate responds to more than orbital geometry alone, with interactions among ice sheets, oceans, greenhouse gases, and other feedbacks shaping the final outcome. For that reason, the comparison between marine isotope stage 11 and marine isotope stage 19 remains one of the most active debates in paleoclimatology. Some scientists regard marine isotope stage 11 as the strongest natural analog for the Holocene. Others believe marine isotope stage 19 provides a closer match despite its shorter duration. Neither interpretation has achieved universal acceptance, and both rely upon careful examination of incomplete geological evidence stretching back hundreds of thousands of years. The most balanced conclusion acknowledges both the remarkable progress and the remaining uncertainty. Researchers broadly agree that the Holocene cannot be judged by age alone, yet they continue to disagree about which ancient interglacial offers the most reliable forecast of its natural future. That uncertainty reflects the complexity of Earth's climate system rather than a failure of science. It also explains why new evidence continues to reshape the discussion. One important step arrived in 2016, when researchers analyzed all 8 of the most recent glacial cycles together and produced a detailed prediction for the natural timing of the Holocene's eventual conclusion. One modern study brought together nearly everything the ice had been preserving for hundreds of thousands of years. Published in 2016 by researchers at the Potsdam Institute for Climate Impact Research in the journal Nature, the work asked a deceptively simple question. If human civilization had never altered the atmosphere, when would the next ice age naturally begin? The team approached the problem by building a climate model capable of reproducing the rhythm of the previous 8 glacial cycles. Instead of matching only one interval, the model successfully recreated repeated advances and retreats of continental ice by combining changes in Earth's orbit with the influence of atmospheric carbon dioxide. The agreement between simulated climates and the geological record suggested that the model had captured the essential processes linking sunlight, greenhouse gases, and the growth of ice sheets across immense spans of time. Its conclusion surprised many people. Even in a completely pre-industrial world, with no factories, no large-scale burning of fossil fuels, and no human-driven rise in atmospheric carbon dioxide, the beginning of the next glacial period would not be expected for at least another 50,000 years. That estimate transformed the way many scientists viewed the present interglacial. The Holocene was already shaping into an unusually long interval between major ice ages through natural causes alone. It is worth lingering on that timescale. 50,000 years extends far beyond recorded history, beyond the first cities, beyond agriculture, beyond every written language that has ever existed. Had the Industrial Revolution never occurred, forests and rivers would still have changed with the seasons. Civilizations would still have risen and fallen, and the great northern ice sheets would still have remained absent. According to this interpretation, the natural clock of glaciation was already set astonishingly far into the future. The explanation begins with Earth's present orbit around the Sunday. Orbital eccentricity is currently very low, meaning the path around the Sun is close to circular instead of noticeably elongated. With less difference between the nearest and farthest points in the orbit, seasonal contrasts become weaker. Combined with the present phase of axial precession, Northern summers are not cooling in the pattern normally associated with persistent snow surviving from one year to the next. Without that survival, continental ice sheets struggle to expand across high latitudes. Seen through this lens, the familiar claim that Earth is overdue for an imminent ice age becomes difficult to defend. The natural timetable indicated by this modeling places the next major glaciation tens of thousands of years ahead, not just beyond a human lifetime, but beyond entire chapters of civilization. The word overdue suggests a missed appointment. The orbital conditions described by the study suggest something very different. Even so, the discussion remains open. Some researchers argue that orbital forcing may exert a weaker influence than the Ganopolsky model assumes, while others question particular feedbacks included in the simulations. Those disagreements are part of normal scientific progress. Even with those differences, multiple independent investigations continue to indicate that the remaining natural lifespan of the present interglacial is measured in several tens of thousands of years, not mere centuries or millennia. Then the story takes an unexpected turn. If nature had already granted the Holocene an exceptionally long future, humanity has not merely entered that timeline. It has begun to reshape it, altering the atmospheric conditions that govern the next chapter before the natural schedule has had the opportunity to unfold. A rhythm that had endured across the quaternary now meets something entirely new. For more than 2 million years, ice sheets advanced and retreated according to the long conversation between Earth's orbit, sunlight, and atmospheric carbon dioxide. That pattern never repeated with mechanical precision, yet its cadence remained recognizable. Today, evidence suggests that the conversation has acquired a new participant. If atmospheric carbon dioxide had remained close to its pre-industrial concentration, the present warm interval would most likely have continued toward a natural glacial inception roughly 50,000 years from now. The picture changes once human emissions are included. According to the 2016 study published in Nature, moderate cumulative human emissions amounting to between 1,000 and 1,500 gigatons of carbon would postpone the next glacial inception by at least 100,000 years. Lead author Andrei Ganopolsky expressed the implication in striking terms. Humanity is, in effect, skipping an entire glacial cycle. Across the approximately 2.58 million year history of the Quaternary glaciation, no comparable interruption appears in the geological record. A climatic rhythm measured in spans approaching 100,000 years may have been altered by industrial activity unfolding across only a few centuries. Set against the age of the planet, that interval is scarcely more than a moment. The mechanism follows directly from the relationship revealed by the ice cores. Atmospheric carbon dioxide raises the baseline temperature of Earth's climate system. As that baseline rises, the amount of reduced summer sunlight required for snow to survive year after year becomes much greater. Even when orbital conditions eventually produce another minimum in northern hemisphere summer insolation, the atmosphere may still contain enough carbon dioxide to prevent permanent ice sheets from taking hold. The snowfall arrives, yet the summers remain warm enough to erase much of what winter creates. Ganopolsky also emphasized the extraordinary longevity of this influence. By burning fossil fuels over a comparatively brief chapter of history, humanity affects climate for at least 100,000 years, and perhaps even longer. Carbon dioxide does not disappear once released. Oceans, soils, vegetation, and rocks gradually absorb it, though those processes unfold across many different timescales. A meaningful fraction remains in the atmosphere for tens of thousands of years, extending its influence far beyond the societies that produced it. This persistence carries an unfamiliar consequence. 50,000 years from now, long after present nations, languages, and monuments have changed beyond recognition, some of the carbon dioxide released during the Industrial Revolution and the centuries that followed is expected to remain aloft. Even 100,000 years into the future, a portion may still shape the climate inherited by distant descendants or by whatever forms of life share Earth at that time. The scale of that legacy resists ordinary comparison. Between roughly 1750 and the present, humanity may have altered the timetable that guided repeated ice ages across the recent geological past. The familiar sequence of advancing glaciers, retreating ice, and returning warmth may no longer arrive when orbital cycles alone would once have invited it. A planetary rhythm written over countless generations has been revised within the span of recorded history, leaving a signature likely to outlast every civilization that has ever stood beneath the changing sky. Another possibility enters the story from a direction few would expect. It begins with fields, villages, and the first people to shape landscapes with their own hands. In 2003, William Rudiman, a paleoclimatologist at the University of Virginia, proposed an idea that challenged the traditional timeline of human influence on climate. The proposal remains controversial, yet it continues to provoke careful discussion because it emerged from an unexpected pattern preserved inside the ice itself. While examining ice core records, Rudiman noticed that the Holocene seemed to diverge from earlier interglacial periods. During previous warm intervals, atmospheric carbon dioxide and methane generally drifted downward as thousands of years passed, following the gradual evolution of Earth's orbit. The Holocene behaved differently. Atmospheric carbon dioxide began rising again around 8,000 years ago, while methane reversed direction roughly 5,000 years ago. Those increases appeared long before steam engines, coal-fired factories, or modern industry entered the picture. Rudiman suggested that the explanation lay in the earliest chapters of agriculture. As farming spread across parts of the Fertile Crescent, Europe, and Asia, forests were cleared to create fields and grazing land. Trees that once stored carbon disappeared, allowing additional carbon dioxide to enter the atmosphere. Later, the expansion of flooded rice cultivation released increasing amounts of methane. Each individual settlement contributed only a small amount, yet those changes accumulated steadily across thousands of years as farming communities multiplied from one generation to the next. If that interpretation proves substantially correct, the beginning of humanity's influence on climate reaches far deeper into history than the Industrial Revolution. Instead of starting around 1750, the process would extend back approximately 8,000 years, when the earliest farming societies began reshaping ecosystems on a continental scale. The atmosphere would have been responding, almost imperceptibly, to countless small decisions repeated across centuries, each field cleared and each wet rice harvest adding another faint trace to a global pattern. Many paleoclimatologists remain unconvinced. They argue that the unusual behavior of carbon dioxide and methane during the Holocene can be explained through natural feedbacks involving oceans, wetlands, vegetation, and changing orbital conditions. In this view, the departures from earlier interglacials do not require widespread human influence. Evidence continues to be gathered, models continue to improve, and the discussion remains active. No broad, scientific consensus has accepted the hypothesis as established fact, though neither has it disappeared from serious investigation. Its importance reaches beyond the debate itself. If Rudiman is even partly correct, then the familiar idea that Earth is overdue for another ice age becomes more complicated still. The Holocene may already have been nudged away from its purely natural path thousands of years before factories, automobiles, or electricity. Human influence would not have begun abruptly. It would have emerged gradually, almost invisibly, through ordinary acts of cultivation repeated across many civilizations and many lifetimes. That possibility changes the perspective from which the entire question is viewed. Orbital cycles still establish the broad framework within which ice ages begin and end. Yet the atmosphere appears capable of amplifying, delaying, or reshaping those orbital influences. Carbon dioxide, whether supplied by natural processes or altered through human activity, may determine whether favorable orbital conditions remain only a possibility or become the beginning of another age of expanding ice. Earth's long climate rhythm depends on more than a single force. Orbital cycles provide the steady pacing, gradually altering how sunlight is distributed across the planet through tens of thousands of years. Carbon dioxide responds within that rhythm, strengthening changes already underway. One sets the tempo, the other increases or softens the intensity. Together, they shape the repeated advance and retreat of continental ice across the Quaternary glaciation through a relationship that scientists continue to examine with increasing precision. The process begins when orbital conditions produce cooler summers across the high northern latitudes. Snow that survives one summer remains through the following winter, slowly compressing into ice. As oceans cool, they absorb larger amounts of carbon dioxide because colder water can hold more dissolved gas. Atmospheric carbon dioxide gradually declines, weakening the greenhouse effect. Lower temperatures allow additional snow to survive. Expanding ice reflects a greater share of incoming sunlight back into space through the albedo effect. Each step reinforces the next, creating a chain of connected feedbacks that encourages further cooling and continued ice sheet growth. The sequence also works in the opposite direction. When orbital variations increase summer warmth, the first changes may be modest. A small reduction in ice cover exposes darker ground and open water, both of which absorb more sunlight than bright ice. Oceans begin warming and release part of the carbon dioxide they had previously stored. Atmospheric carbon dioxide rises, strengthening the greenhouse effect and adding further warmth. More ice melts, exposing still more dark surfaces. Once again, each process supports the next. Though the initial push came from changing orbital geometry rather than carbon dioxide alone, ice cores revealed an important detail that first appeared confusing. During several glacial transitions, temperature began changing before atmospheric carbon dioxide reached its highest or lowest values. The delay ranged from several hundred to a few thousand years. At first glance, this seemed to imply that carbon dioxide played only a secondary role. Continued research produced a more complete picture. Orbital forcing initiates the climate shift, while carbon dioxide magnifies and sustains it. Each influences the other through continuous feedback, making the relationship bidirectional instead of one directional. Another principle follows from that understanding. Building a new ice age requires more than reduced summer sunlight. Atmospheric carbon dioxide must also fall beneath a threshold that allows snow to survive year after year. When prolonged periods of weak summer insolation occur across the northern hemisphere, surviving snow gradually transforms into expanding ice sheets. If atmospheric carbon dioxide remains elevated, even orbital minimums can leave summers warm enough to remove much of that seasonal snow before lasting ice has the opportunity to spread. The pattern echoes a mechanism encountered much earlier in Earth's history. During the Snowball Earth episodes, increasing ice reflected more sunlight, strengthening planetary cooling until frozen landscapes reached extraordinary distances. The same albedo feedback still exists today because it is rooted in the basic physics of light and ice. Nothing about that process has disappeared. What has changed is the atmosphere surrounding it. Elevated carbon dioxide raises the temperature baseline, making it far more difficult for that familiar cascade of expanding ice to begin under present conditions. Eventually, orbital cycles will continue their patient progression, as they always have. If the conditions for widespread glaciation return far in the future, the process will unfold through landscapes already shaped by modern civilization, placing cities, coastlines, and human geography into a climate story unlike any our species has yet experienced. A new ice age would arrive with extraordinary patience. Its opening chapter would pass unnoticed within a single lifetime, and perhaps within many generations. The first changes would unfold across thousands of years, each one almost too small to recognize on its own. Climate records would reveal the pattern long before daily experience could. Even so, those gradual shifts would accumulate, each season adding another layer to a transformation measured on the scale of geology. The earliest signal would not be overwhelming cold. It would appear in the character of summer across the high northern latitudes. Regions including Canada, Scandinavia, and Siberia would experience cooler growing seasons that ended a little sooner than before. Winter snow would linger farther into the warm months. Patches surviving through July would become increasingly common. Those surviving fields of snow would compress into dense ice, feeding glaciers that would begin advancing instead of retreating. The landscape would change through persistence rather than speed. Century after century, those surviving snowfields would deepen. Fresh snowfall would settle upon older layers that never completely disappeared. As bright surfaces expanded, they would reflect a larger share of incoming sunlight back into space. That increase in planetary reflectivity, known as the albedo effect, would encourage additional cooling, allowing even more snow to endure each summer. At first, the process would seem restrained. Eventually, the feedback would strengthen itself, giving larger ice sheets the conditions needed to continue growing without interruption. The consequences would spread outward from those northern centers. Scandinavia would stand among the earliest heavily populated regions to encounter expanding continental ice. Across North America, glaciers resembling the Laurentide ice sheet would gradually reclaim the Canadian shield. During the last glacial maximum, that immense body of ice extended south to approximately latitude 37 degrees north, covering more than 33 million square kilometers, which is about 13 million square miles. Its frozen reach stretched beyond present-day Columbus, Ohio, and farther south than present-day Denver, Colorado. The Great Lakes region would eventually disappear beneath an enormous blanket of moving ice. Human societies would experience profound changes long before glaciers reached their cities. Agriculture depends upon reliable growing seasons, and those seasons would steadily shorten across temperate regions. Grain-producing landscapes in Canada, northern Europe, and much of northern Asia would harvest smaller yields with each passing century. Communities would gradually shift cultivation toward lower latitudes where warmer summers continued. Migration would follow changing harvests long before advancing ice required it, reshaping economies and settlement patterns across continents. Oceans would respond as increasing volumes of water became locked inside continental ice sheets. Within roughly 10,000 years after glacial conditions became firmly established, global sea level could fall by about 61 meters, which is about 200 feet. Former coastlines would extend outward, exposing broad plains where shallow seas once rested. Rivers would carve new paths across that emerging land, while plants and animals expanded into environments that had remained underwater for thousands of years. The resulting planet would not become uniformly frozen. Atmospheric circulation would reorganize, redirecting rainfall into different regions. Some equatorial landscapes could receive greater precipitation than today, and portions of the Sahara might once again support extensive grasslands. Earth would reorganize its climates instead of covering every horizon with ice. For now, that immense transformation remains suspended, held back by conditions that have altered the timetable itself. One of the most unexpected discoveries in climate science is also one of its most difficult ideas to hold all at once. The carbon dioxide released through human activity is driving a rapid warming of the modern world. Across a much longer span of geological time, that very same increase in atmospheric carbon dioxide is also creating a barrier against the next natural ice age. Both statements can be true together because they describe different clocks operating within the same planetary system. That paradox does not change the urgency of the present. The warming already unfolding is reshaping coastlines through rising seas, increasing the likelihood of damaging heat, altering rainfall patterns, placing additional strain upon food production, and accelerating the loss of many ecosystems that developed during the stable climate of the Holocene. These consequences belong to the lives of people living now, along with generations still close enough for their descendants to imagine. They unfold across decades and centuries, a pace that matters directly to every society on Earth. The delayed return of glaciation belongs to an entirely different scale of time. Current research suggests that natural conditions favorable for a new continental ice sheet would otherwise have appeared tens of thousands of years from now. Human emissions have shifted that timetable much farther into the future, perhaps delaying glacial inception for around 100,000 years under some modeled scenarios. Those distant consequences exist within geological history, far beyond any practical horizon for modern civilization. No responsible approach to climate policy would accept severe damage in the present as a trade for a possible benefit so unimaginably far ahead. Climate researchers have expressed this distinction plainly. Several have noted that the next ice age deserves far less immediate attention than the human caused warming already taking place. Andrei Ganopolsky, whose modeling work helped reshape discussion of future glaciation, summarized the situation with equal clarity. Right now, the challenge is global warming, not global cooling, and reducing carbon dioxide emissions remains the necessary response. The unusual role of carbon dioxide within the distant glacial cycle does nothing to weaken that conclusion. Even so, the paradox itself deserves recognition because it reveals how closely Earth's systems are connected. Orbital cycles, ocean circulation, atmospheric chemistry, expanding forests, shrinking glaciers, and reflective ice never operate in isolation. Alter one element, and the effects spread outward through the rest. The atmosphere does not separate changes according to whether they are convenient for human timescales. Physical processes continue interacting according to the same principles that governed them long before our species appeared. There is another layer to this story that reaches beyond measurements and computer models. Throughout every chapter of recorded history, before the Industrial Revolution, the eventual return of continental ice belonged to the background rhythm of the planet. The uncertainty centered upon timing, never upon whether the rhythm itself would continue. Each previous glacial cycle eventually yielded to another. That expectation shaped the entire Quaternary glaciation, extending across roughly 2,580,000 years. Today, the rhythm itself appears less certain than before. Human activity has introduced a new influence into a cycle once governed entirely by natural forces. Whether that interruption ultimately lasts one glacial cycle or much longer remains an active subject of research. At the heart of that uncertainty lies another puzzle, one that reaches beyond the Holocene itself and into the deeper mystery of why Earth's ice ages settled into their familiar 100,000-year rhythm at all. A deeper puzzle waits beneath nearly every discussion of ice ages. It does not concern the next glaciation alone. It asks why the entire rhythm of Earth's climate changed in the first place. Around 800,000 years ago, the planet settled into a pattern dominated by glacial cycles lasting roughly 100,000 years. Before that turning point, the major advances and retreats of continental ice followed a much shorter rhythm of about 41,000 years. Something fundamental shifted, yet the reason remains one of paleoclimatology's greatest unsolved problems. At first glance, the change seems difficult to explain. Earth's orbital eccentricity, the gradual alteration in the shape of its path around the Sun, follows a cycle close to 100,000 years. That timing matches the newer glacial rhythm surprisingly well. The complication is that eccentricity changes the amount of incoming solar energy only slightly. Obliquity, the gradual change in Earth's axial tilt, creates a much stronger influence upon high-latitude summers and follows the earlier 41,000-year pattern. The stronger signal appears to have surrendered its leading role to a weaker one, leaving scientists searching for the mechanism that allowed such a transition. Several explanations have emerged, each supported by evidence yet incomplete on its own. One proposes that marine-based ice sheets gradually became capable of much larger collapses and reorganizations. As repeated glaciations carved continental shelves and reshaped coastlines, enormous ice masses resting upon the ocean floor may have developed new forms of instability. Once those conditions existed, each major glaciation could grow deeper before finally breaking apart, naturally stretching the interval between full ice ages. Another idea focuses upon atmospheric carbon dioxide. Across millions of years, natural geological processes slowly reduced the average concentration of carbon dioxide in the atmosphere. Eventually, a critical threshold may have been crossed. Ice sheets could then survive longer, expand farther, and accumulate enough mass to respond more strongly to the slower eccentricity cycle than to changes in axial tilt alone. Under this view, orbital cycles continued providing the timing, while atmospheric chemistry altered which rhythm became dominant. A third proposal examines the ground beneath the glaciers themselves. Early continental ice sheets rested upon thick layers of loose sediment known as regolith. Repeated advances gradually scraped much of that material away, exposing harder bedrock across broad regions. That transformation changed how glaciers gripped the land, how rapidly they flowed, and how difficult they became to remove once established. Small differences at their base may have produced much larger differences across entire ice sheets. These competing ideas share an important lesson. The broad framework of glacial timing is understood remarkably well, yet some of the deepest controls remain under active investigation. Modern climate models reproduce many features of Earth's glacial history with impressive accuracy, but uncertainty still exists because the underlying engine has not revealed every detail of its design. That uncertainty does not weaken the science, it reflects its honesty. Researchers continue testing competing explanations, comparing sediment records, ice cores, ocean deposits, and increasingly sophisticated simulations. Many of the largest questions surrounding Earth's frozen past have found convincing answers. A few still stand open, marking the frontier where understanding continues to grow. From that frontier emerges another perspective, one concerned less with the global average than with the different ways future glaciation could unfold across individual regions of the world. A glacial world does not spread across Earth like an evenly drawn blanket. Its influence unfolds unevenly, shaped by geography, ocean currents, mountain ranges, and the arrangement of continents. Although global temperatures decline, each region follows its own path through that transformation. Some landscapes become buried beneath expanding ice. Others experience shifting rainfall, changing coastlines, or altered growing seasons long before any glacier appears. The greatest burden falls across the northern hemisphere. Most of Earth's continental land lies there, providing broad surfaces where snow can accumulate year after year. High latitude summers determine whether winter snow survives or disappears, making these regions the primary control point for glacial beginnings. Canada, Northern Europe, and much of Russia become the stage upon which continental ice sheets gradually emerge. As the frozen masses expand, they reshape rivers, redirect winds, and alter the climate far beyond their own boundaries. Far closer to the equator, the story becomes more varied. Lower global temperatures reduce evaporation from many ocean surfaces, while shifting atmospheric circulation changes the routes followed by seasonal rains. Some tropical and subtropical regions could receive greater rainfall than they experience today. During the last glacial maximum, evidence preserved in lake sediments and ancient shorelines suggests that parts of what is now the Sahara supported more lakes, grasslands, and wildlife than the desert familiar today. A cooler planet does not produce universal dryness. It redistributes moisture according to an entirely different pattern. Other places move in the opposite direction. The American Southwest and the lands surrounding the Mediterranean Sea would probably become much drier as immense northern ice sheets altered the position of major storm tracks. Rain-bearing systems that now nourish these landscapes could shift elsewhere, leaving longer dry seasons and reducing freshwater supplies. Agriculture would change long before advancing glaciers reached those latitudes, illustrating that climatic consequences often arrive well ahead of the ice itself. The oceans would also participate in this planetary reorganization. As glaciation strengthened, the Great Thermohaline Circulation, often described as the global ocean conveyor belt, would likely slow. That immense network of sinking and rising seawater carries heat from equatorial regions toward higher latitudes. Any significant reduction changes sea surface temperatures, influences fisheries, redirects storms, and reshapes rainfall across continents separated by thousands of kilometers, which is about 621 miles. Every coastline becomes connected through water moving beneath the surface. South of the equator, the experience differs again. Antarctica would continue storing additional ice, yet the southern hemisphere contains relatively little land at high latitudes compared with the north. Large continental ice sheets, similar to those that once covered North America, have few places to develop outside Antarctica itself. Cooling would spread broadly, although widespread burial beneath advancing glaciers would remain largely a northern hemisphere phenomenon. Across Southeast Asia, falling sea levels would reveal an older geography. During the last glacial maximum, the shallow Sunda Shelf emerged above the ocean, connecting much of mainland Southeast Asia with many islands that are separated today. Forests, rivers, and migrating animals crossed landscapes now covered by shallow seas. A future glaciation could expose those connections once more, creating an unfamiliar map without changing the position of the continents themselves. The precise regional details remain subjects of active research, refined with every improvement in climate models and geological evidence. Even so, the larger lesson already stands with remarkable clarity. Ice ages are never experienced equally. They transform each corner of Earth according to its own geography, leaving every region to write a different chapter within the same planetary story. Across the immense sweep of Earth's past, another pattern gradually comes into view. It is not perfectly regular, nor does it promise the same outcome every time, yet it appears often enough to invite careful attention. Again and again, episodes of profound climatic hardship have been followed by remarkable chapters in the history of life. Ice has repeatedly narrowed the possibilities available to living organisms. When the frozen grip eventually loosened, evolution often answered with unexpected creativity. The oldest and perhaps most striking example reaches back to the era when glaciers spread across nearly the entire planet. After Snowball Earth finally released its hold, oceans and coastlines became settings for one of biology's greatest transformations. Within the geological interval leading into the Cambrian explosion, animal life diversified at a pace unmatched in earlier history. New body forms appeared, unfamiliar ecological relationships emerged, and evolution began exploring possibilities that had remained unrealized for hundreds of millions of years. The frozen world did not create those organisms directly, yet the environmental reset that followed may have opened opportunities unavailable before. A different chapter unfolded during the Carboniferous and Permian glaciations. As climates fluctuated across continents, vertebrate lineages encountered new challenges that rewarded flexibility and endurance. Among them were the synapsids, distant relatives whose adaptations gradually separated them from other groups of land animals. Across countless generations and through many changing environments, those lineages accumulated traits that eventually led toward mammals. The path was neither straight nor inevitable, but its earliest steps were taken in a world repeatedly shaped by advancing and retreating ice. Far more recently, the Pleistocene brought another series of climatic oscillations. Human ancestors never experienced a stable background climate for long. Habitats shifted, coastlines moved, familiar food sources disappeared, and migration routes changed with remarkable persistence. Many researchers propose that these repeated environmental pressures contributed to an evolutionary competition among different members of the genus Homo, planning beyond the present season, sharing knowledge across generations, strengthening social cooperation, and developing increasingly sophisticated tools all became valuable advantages in landscapes where conditions rarely remained constant for long. None of this suggests that glaciation is universally beneficial. The geological record preserves many losses alongside its innovations. Entire ecosystems vanished. Countless species disappeared forever. The extinction of much of the Great Ice Age megafauna reminds us that climatic stress can overwhelm even successful organisms. Evolution does not reward every lineage equally. It preserves those capable of adapting, while many others fade into the fossil record. Resilience emerges through relentless selection, carrying both creation and loss within the same process. That longer perspective invites an unfamiliar thought. For hundreds of millions of years, recurring ice ages acted as one of the great architects of biological change. They repeatedly reshaped habitats, redirected migration, and altered the conditions under which natural selection operated. If humanity has truly delayed that ancient rhythm, then one of Earth's oldest evolutionary influences has also been altered. No scientist can yet determine how a biosphere responds when such a persistent source of environmental pressure is postponed for tens of thousands of years. The question remains open because the experiment has only just begun. Human history occupies little more than an instant beside Earth's geological record. Yet, within that instant, our species may already have modified a cycle that influenced life across continents and oceans for ages beyond ordinary imagination. Predictions about Earth's future are often imagined as bold certainties stretching across immense spans of time. The reality is more careful. Climate scientists build their expectations from observations, physical laws, ice cores, sediments, orbital calculations, and computer models that are continually refined as new evidence appears. The picture that emerges is neither absolute nor speculative fantasy. It is a measured assessment of probabilities, shaped by everything the planet has already revealed about its own history. When researchers ask when the next natural glaciation would begin, they first imagine a world untouched by modern industrial emissions. Under those conditions, the leading orbital analog studies suggest that the next major expansion of continental ice would most likely begin somewhere between 50,000 and 100,000 years from now. The precise timing depends upon which ancient interglacial provides the closest comparison, along with the carbon dioxide threshold assumed within each climate model. Those differences matter, yet they all point toward a future measured in geological time, not human lifetimes. Adding modern atmospheric carbon dioxide changes that picture substantially. Across multiple modeling studies, the elevated concentration of greenhouse gases delays the conditions required for glacial inception. Current estimates indicate that the beginning of the next full glaciation is unlikely before roughly 100,000 years from now, and possibly later if atmospheric carbon dioxide remains elevated for extended periods. Some researchers conclude that the present interglacial may become the longest experienced during the entire Quaternary Ice Age, with the probability of renewed continental ice forming during the next 100,000 years greatly reduced by humanity's alteration of the atmosphere. These conclusions remain bounded by important limits. Every model is calibrated against climates preserved in Earth's past, because that record provides the only laboratory spanning millions of years. Future conditions may eventually move beyond anything preserved within those natural archives. Carbon cycle feedbacks, long-term ice sheet behavior, and climatic tipping points are areas of active investigation. As projections extend beyond 50,000 years, uncertainty steadily widens. The broad direction remains scientifically supported, while the precise timetable becomes increasingly difficult to define. Alongside those distant projections stands another conclusion supported with far greater confidence. The warming expected over the coming century, and continuing across the next millennium, is driven primarily by human emissions of carbon dioxide. Rising seas, changing rainfall, increasing heat extremes, shifting ecosystems, and growing pressure upon food production belong to timescales that overlap with existing civilizations. These consequences unfold within years, decades, and centuries, making them fundamentally different from the distant rhythm of natural glacial cycles. Placed together, these findings reveal a remarkable perspective. Humanity is not approaching the edge of another ice age. Instead, civilization exists within an unusually warm interval whose duration now appears to have been extended by its own influence upon atmospheric chemistry. The same actions reshaping climate today may also have postponed the return of continental ice far beyond what earlier generations of scientists once expected. Across centuries, millennia, and geological ages, the future now carries traces of choices made during a remarkably brief chapter of Earth's history. That realization settles into the story with unusual weight. A species that learned to extract and burn fossil fuels over only a few centuries may have shifted a planetary rhythm that endured for hundreds of thousands of years, leaving its signature upon a future that stretches far beyond any civilization yet imagined. There are moments when the numbers become so large that they seem to lose their meaning. They drift beyond ordinary experience, beyond memory, beyond history itself. The story of ice ages has gradually carried us into that immense landscape where the passage of time is measured not by generations or civilizations, but by the slow turning of the planet through cycles that began long before humanity learned to leave footprints in stone. Climate modeler Andrei Ganopolsky expressed that scale with striking clarity. By burning fossil fuel over just 1 century, we will affect climate for at least 100,000 years, or even more. Those words compress an extraordinary imbalance between cause and consequence. A brief interval of industrial activity reaches forward across a span of time that exceeds the entire written history of civilization by many thousands of years. 100,000 years ago, Homo sapiens had only recently begun expanding beyond Africa. Neanderthals still walked across parts of Europe and Western Asia. The painted chambers of Lascaux lay about 60,000 years in the future. Farming remained nearly 90,000 years away. The Roman Empire rested approximately 99,700 years beyond that distant horizon. Every kingdom, every language, every invention, every library, every city known today belongs to a remarkably thin layer within that immense stretch of time. The carbon dioxide already released into the atmosphere does not recognize those human milestones. A portion of it will continue influencing Earth's energy balance across spans that extend toward another 100,000 years. Continents will continue their gradual motion, rivers will alter their courses, coastlines will evolve, species will appear and disappear. Through all of those changes, part of the atmospheric alteration created during the industrial era may still remain woven into the climate system. Ganopolsky reflected on that realization with equal restraint. It is mind-boggling that humankind is able to interfere with a mechanism that shaped the world as we know it. The statement does not diminish the complexity of climate science. Instead, it acknowledges the remarkable reach of a species that has become capable of influencing processes once thought untouchable by any living creature. The orbital rhythms first calculated by Milankovitch while working through mathematics during the First World War have guided Earth's long climate story throughout the approximately 2,580,000 years of the Quaternary Ice Age. They accompanied every glacial advance and every warmer interval between them. Their influence formed the environmental backdrop for migrations, extinctions, evolutionary innovation, and the landscapes inherited by humanity. Those orbital cycles continue today, exactly as celestial mechanics predicts. Earth still tilts, wobbles, and follows its changing path around the sunday. What appears to have changed is the climate system's response. Atmospheric carbon dioxide may have raised the threshold required for those familiar rhythms to awaken another great continental glaciation. The mechanism has not vanished, yet its outcome may have been postponed for at least one complete cycle by a species that has existed for only about 300,000 years. That possibility carries consequences reaching beyond climatology. Geologists continue debating whether human activity has become influential enough to justify recognizing a new geological epoch, often called the Anthropocene. Among the strongest arguments is the growing evidence that humanity now alters Earth's physical systems on a planetary scale, leaving signatures that future rocks, ice, and sediments may preserve long after our own civilizations have faded. Earth is about 4,500,000,000 years old. Across that immense lifetime, it has endured events that seem almost impossible when measured against the scale of human history. Asteroids have struck with enough force to transform continents. Great volcanic outpourings have altered the atmosphere for ages beyond memory. Ice has spread across much of the planet more than once. Entire branches of life have disappeared, while others emerged from the aftermath. Through every upheaval, the planet itself continued its long journey around the Sunday. This perspective changes the meaning of resilience. In geological terms, Earth is not a delicate world balanced upon the edge of failure. Its climate is a dynamic system shaped by countless interacting processes, each pushing and pulling against the others across immense spans of time. Oceans exchange heat with the atmosphere. Rocks slowly absorb carbon dioxide through weathering. Volcanoes return gases from the interior. Living organisms reshape air, soil, and sea. Disturbances can be profound, yet the system has repeatedly settled into new forms of habitability. The conditions change, while the planet endures. About 66 million years ago, a large asteroid struck what is now the Yucatan Peninsula. The consequences spread across the globe. Dust and aerosols dimmed sunlight. Food webs collapsed. Roughly 75% of all known species disappeared. The great non-avian dinosaurs vanished, alongside countless marine organisms and plants. Even so, the story did not end there. Within a few million years, the surviving mammals diversified into forms that occupied forests, grasslands, rivers, mountains, and eventually the skies. Ecological spaces left empty by extinction became opportunities for new evolutionary paths. The great ice ages tell a similar story through a different rhythm. During the approximately 2,580,000 years of the Quaternary Ice Age, glaciers advanced and retreated again and again. Landscapes shifted with each cycle. Rivers changed course. Forests expanded and contracted. Animals migrated, adapted, or disappeared. Many lineages endured by changing their behavior, physiology, or range. Others gave rise to descendants better suited to altered conditions. The repeated return of ice did not strip Earth of life. It became one of the forces shaping life's remarkable diversity. That enduring resilience, however, belongs to the planet, not automatically to every species living upon it. Earth can recover from transformations that unfold over millions of years because geological time provides opportunities for ecosystems to reorganize and evolution to explore new possibilities. Individual species do not possess that luxury. Every organism depends upon environmental conditions that fall within certain limits. When those limits shift too rapidly or too far, survival becomes uncertain, no matter how resilient the broader planet may be. Human civilization arose during the unusual climatic stability of the Holocene. Agriculture, permanent settlements, written language, and complex societies all developed within that relatively steady interval. Our cities, food systems, and infrastructure reflect those conditions. Earth itself will continue whether that stability persists or fades. Oceans will still circulate. Mountains will still rise and erode. New species will appear while others vanish. Viewed from that longer horizon, The enduring question is not whether Earth will survive. Its history offers that answer many times over. The deeper uncertainty concerns the world that follows this chapter, and whether the civilization now capable of altering planetary systems will remain part of the landscape that future Earth continues to shape. There is a particular kind of perspective that arrives only after spending time with deep history. It asks nothing of us. It offers no lesson wrapped in certainty. It simply places a human lifetime beside the age of the world and allows the comparison to exist. In that comparison, familiar scales begin to dissolve. The calendar that measures our days becomes almost transparent against the rhythms that have shaped Earth for ages beyond imagination. Every fact gathered along this journey points toward the same realization. Written history reaches back roughly 5,000 years. The Holocene has lasted about 11,700 years. The present Quaternary Ice Age has endured for approximately 2,580,000 years. Earth itself is about 4,500,000,000 years old. Each step outward enlarges the frame until entire civilizations become brief passages within a story that continues almost untouched by their arrival or departure. Holding those spans together creates an unusual sensation. It carries traces of wonder, yet it also resists easy description. The feeling comes from recognizing how slender the platform of civilization truly is. Languages, kingdoms, libraries, monuments, discoveries, and generations have unfolded during an interval that barely registers within the longer rhythms of climate. The stability that allowed fields to be planted and cities to rise occupies only a narrow chapter inside a cycle that is repeated many times before our species learned to write its own history. Long before the first human voice echoed across a landscape, advancing and retreating ice had already been reshaping continents. Glaciers carved valleys that later carried rivers. Falling seas exposed land bridges that guided migrations of animals, followed eventually by our own ancestors. Climatic shifts opened some habitats while closing others. The diversity inherited by mammals emerged through pathways cleared by older extinctions and older transformations. Many of the conditions that eventually made civilization possible were prepared by cycles of cold that had been unfolding for millions of years before any human observed the stars or imagined the future. Against that background, the present moment acquires an unfamiliar scale. Through the burning of fossil fuels over only a few generations, humanity has altered atmospheric carbon dioxide enough to influence processes that once appeared governed solely by orbital mechanics and geological time. The earliest furnaces of the Industrial Revolution were built without any understanding that their emissions would accumulate across centuries. No one standing beside those fires could have imagined that they were participating in an experiment reaching far beyond recorded history. That realization is neither accusation nor celebration. It is a statement about consequence. A species that has existed for roughly 300,000 years has become capable of influencing systems that operated for approximately 2,580,000 years with remarkable persistence. Such influence arrived long before wisdom about its full implications. Seen through the lens of deep time, the present age becomes extraordinary for reasons unlike those found in ordinary history. We happen to live during an interval when one species has begun to reshape the cadence of an entire planetary process. Whether future ages remember this moment as a brief disturbance or the beginning of a lasting transformation remains part of the story that Earth continues to write. At the beginning of this story, a single word carried an enormous promise: overdue. It sounded precise, almost mechanical, as though Earth possessed a calendar with marked dates waiting to be reached. After following the long path through orbital cycles, shifting ice, atmospheric chemistry, and the history written into stone, that word appears differently. The planet has patterns. It does not keep appointments. A true clock repeats with dependable regularity. Every movement follows the one before it. Earth's glacial rhythm has never behaved so simply. The return of continental ice depends upon the meeting of several conditions at once. Orbital geometry changes the seasonal distribution of sunlight. Atmospheric carbon dioxide alters how much heat remains within the climate system. Expanding snow and ice brighten the planet, reflecting more sunlight back into space. Ocean circulation redistributes warmth between latitudes. Each influence strengthens or weakens the others, producing a system that behaves more like an intricate conversation than a countdown. The age of the present interglacial is only one piece of that conversation. The Holocene has now lasted about 11,700 years. Some earlier interglacials reached their conclusion after shorter intervals. Others endured considerably longer. Looking only at age gives the impression that a familiar ending should already have arrived. Looking at orbital configuration tells another story. Looking at atmospheric carbon dioxide tells another still. No single measurement can determine the future of a system built from many interacting parts. That is why the simplest version of the question has no equally simple reply. Judged only against the duration of some previous warm intervals, the present climate has reached an age at which earlier interglacials occasionally gave way to renewed glaciation. Judged through the combined influence of orbital geometry and pre-industrial atmospheric carbon dioxide, the most likely natural beginning of the next major glaciation remained roughly 50,000 to 100,000 years away. Judged by today's concentration of atmospheric carbon dioxide, many researchers conclude that the next widespread growth of continental ice has likely been postponed to at least 100,000 years into the future, and perhaps beyond. Even so, the intuition behind the word overdue is understandable. It recognizes that the warmth surrounding civilization is part of something much larger. The present world exists within an ice age that has alternated between colder and warmer chapters for approximately 2,580,000 years. Our forests, coastlines, rivers, and cities occupy one interval within that continuing sequence. The pattern itself has never disappeared from the story of Earth. Perhaps the difficulty lies in expecting a single word to describe a system of remarkable complexity. Overdue suggests certainty where evidence instead points toward probability. It compresses orbital mechanics, atmospheric chemistry, ice dynamics, and geological feedback into a conclusion that the science cannot honestly make. The larger pattern remains. The precise schedule does not. A gentler description may serve better. We are living within a warm interval inside a longer age of ice. That interval will eventually give way to another chapter under some future combination of orbit, atmosphere, and planetary feedbacks. What remains uncertain, and unlike anything known from the previous 2,580,000 years, is how deeply humanity has already become part of the mechanism itself. The oldest witnesses to this story have never spoken a word. They rest beneath the great ice of Antarctica, where each layer preserves another season, another snowfall, another breath of an atmosphere long vanished. Within tiny bubbles sealed inside that frozen record lies air from ages before our species existed. Those bubbles do not speculate or remember imperfectly. They preserve the chemistry of worlds that warmed, cooled, and changed long before the first human eyes lifted toward the stars. Those records reveal landscapes no civilization has ever known. They describe a planet held in the grip of full glaciation, where continental ice stretched across immense distances, reaching toward horizons more than 1,600 kilometers away, which is about 994 miles. Sea level stood around 120 meters lower than today, which is about 394 feet. Coastlines reached far beyond their modern limits. Land bridges connected continents, now divided by open water. Entire migration routes existed where waves now move across submerged plains. None of those places belong to mythology, they belong to Earth. Geological history leaves little doubt that such conditions have returned again and again. They almost certainly will return on sufficiently long timescales. Whether that transition begins roughly 50,000 years from now, 100,000 years from now, or later still depends upon orbital geometry, atmospheric carbon dioxide, and planetary feedbacks whose interactions science continues to refine. The broad pattern remains remarkably clear, even while the exact timing stays beyond complete certainty. There is, however, one difference that separates the present from every earlier warm interval. The species living through this interglacial has become aware that it is an interglacial. We have drilled into ancient ice and recovered its memory. We have traced the changing path of Earth's orbit through space. We have reconstructed climates older than language, older than agriculture, older than our own existence. Piece by piece, we have uncovered the outlines of a mechanism that has shaped the planet for approximately 2,580,000 years. The creatures that crossed frozen grasslands never knew why the climate changed around them. The mammoths carried no understanding of orbital cycles. The painters who covered cave walls in what is now France left remarkable records of animals and people, yet they possessed no knowledge that immense sheets of ice had sculpted the valleys beyond their homes. They lived within the cycle without recognizing its larger design. Our own position is unlike theirs. We know the mechanism well enough to recognize its rhythm, even while important details remain under investigation. We understand that civilization emerged during an unusually stable interval. We also understand that the atmosphere has become something humanity can influence, altering a process once governed entirely by natural forces. Knowledge alone does not determine the future, it enlarges responsibility. Perhaps that is the deepest lesson carried within the oldest ice. The planet has always been changing. Life has always adapted, diversified, and endured through transformations almost beyond imagination. Now, for the first time, one species understands enough of that history to recognize its own place inside it. The ice has always come back. For the first time in approximately 2,580,000 years, something on this planet may help decide when.